The way to solve material balance analysis depends on how much time will you spend on that problem, especially in exams. And for that, in this video, I will present the complicated concept of reactive systems in just 5 or 6 minutes. Generally speaking, when you have a material balance problem, then you start with the flowchart, labeling all the information, and then degrees of freedom analysis. Now, the third step is degrees of freedom analysis. It is itself another story. Leave the degrees of freedom to another video. This is because each of the 3 methods has its own degrees of freedom analysis. The variables you will need to calculate the degrees of freedom analysis using the molecular balance is the number of independent chemical reaction, the number of independent reactive species, and the number of the relations that are given in the question. For example, if you have 3 reactions together and then you try to reach to the third one by adding and multiplying the first to the second one, or the opposite, then if you can reach to the third chemical reaction, then it means you have only 2 independent reactions, because one reaction will depend on the 2. That's the meaning of the independent reactions. But if you have, for example, 2 reactions or 3 reactions and you cannot reach to all of them together by adding, multiplying, then all of the 3 will be independent chemical reactions. The meaning of the independent reactive species is if you have, for example, a ratio of 2 to 1 from molecule of A to molecule of B in one stream, then it shouldn't be equal to the same ratio in other stream. If it is equal, then it will be dependent reactive species. So you'll choose one of the molecules as independent reactive species. The question is when to use the molecular species balance. It is only useful when you have only one single reaction, which means you can depend on conversion to calculate what comes and leaves out of the reactor. If it is more than one reaction involved, it will be more complicated and it will cost you a lot of time to solve one tiny or simple problem, which is the opposite objective of the video, the saving of time. The extent of reaction method, we kind of introduced it before. We used it to solve one reactive system. It's in this video if you want to see it. What we didn't do is to calculate the degrees of freedom analysis for that problem. It is the number of unknowns, number of independent chemical reaction, the same concept, number of independent reactive species and number of independent non-reactive species, and then the number of relations. The new thing in the extent of reaction method is the number of non-reactive species. It means if you have a ratio between one molecule to the other molecule that do not participate inside the reaction, then the ratio in one stream, it shouldn't be equal to all the ratios in any other stream located in the same flowchart. Otherwise, if one stream at least has the same ratio, then it will depend, and we will consider one of the molecules to be independent non-reactive species. The extent of reaction method is better used when you have equilibrium reaction, which means there is a forward reaction and there is a backward reaction. Now, my chemical engineering friend, I saved the best to the last, which is the atomic balance. Not only because it helped me during the exam, but actually because it is depending on what we call the law of mass conservation, the one that is famous, that we cannot explain anymore. It states that mass cannot be generated, cannot be consumed. Atoms cannot be generated, cannot be consumed. If you have a reactive system, if you have a physical system, it doesn't matter. Input will equal to output, assuming steady state assumption. The way to calculate degrees of freedom analysis for the atomic species method is number of unknowns, you know it. Number of relations, you know it. Number of independent non-reactive species, now you also know it. But number of independent atomic species. If you have atoms ratio, not molecule ratio, if you have atoms ratio in one stream is the same at least in one other stream, at least one, then it will be dependent and we will use one of the atoms. Because I'm a fan of learning through examples, I will now solve a problem that will combine the 3 ideas together. Given the feed information and given the fractional conversion of the limiting reactant, using the 100 mole as a basis, we can find the mole amount of each component. We want to find all the molar amounts in this problem, starting with flowchart, labeling, and then degrees of freedom. Starting with atomic balance, particularly calculating the degrees of freedom initially, we can notice from the problem itself that the ratio of carbon to hydrogen, it's not the same because there is a generation of C3H3N. For the number of reactions, we have only one, obviously, so we can only just write one independent chemical reaction. And we can't forget the fact that fractional conversion is used as a relation given in the problem, which will make it also 1. Since we have degrees of freedom 0, we can solve the system. We will find first the mole of C3H6 that left the reactor using the fractional conversion. We will start doing atomic balance specifically on carbon, followed by atomic balance on nitrogen. And then we will do for hydrogen. Lastly, we will do for oxygen. Now we're expecting that if we do the extent of reaction, of course the answer should be the same. And similarly, if we do molecular balance, then you would expect the answer to be the same. Using molecular balance and starting with degrees of freedom, the number of unknowns, the number of independent chemical reaction. Since there is a generation term in the product stream, the ratio, if you take it in the feed stream for any other molecule, it will always be different than the product because of the generation of water and C3H3N. Calculating the degrees of freedom now, it will be 0, which means we can solve the system. We will start with the conversion and we can use it because we have only one single reaction. We have 30% from 10 reacted, which means we have 3 mole reacted. Use the equation that I've written here, feed minus reacted, it will be the remaining that will leave the reactor, and then feed plus the generation, it will be water and C3H3N. For the extent of reaction method, I already did the calculation for the same problem in the previous video, but for the degrees of freedom analysis, there is the number of molecular independent non-reactive species. We have only the nitrogen inert, and we have the number of independent reactive species, which will be in this case those which participate in the reactor, and they are 5, making the degrees of freedom 0, which means we can solve the unit. I'm sure you noticed that I didn't spend a lot of time solving, more than I spent explaining the concept. This is because for me as a student, I didn't enjoy someone teaching me how to solve, but I did enjoy how to find the ideas and how to make them connected with one another. If you made it to the last of the video, I hope, just take the hints that I shared, take the degrees of freedom that I wrote, and then solve a problem step by step. If there is something hard, just leave it in the comment and I will answer it very fast. Good luck.